Alright, time for another DraftPhysics.com video presentation. What the hell happened there? Alright, it's recording. Yeah, can't trust this thing sometimes. Anyway, so this is the second effort at making this video because the software is a little buggy. Blah, 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 blah. So anyway, this guy called Dirty Garage Guy. Yeah, appears to be the channel name. Anyway, it's physics without the nerdy bullshit, and so that's kind of appealing. It's foreign, British, so I'll have to interpret now and then, and so maybe he can be provoked into, an argument. This kind of guy, maybe you could force him, to defend his honor, or something like that. Who knows? Maybe he doesn't mind fighting now and then. But anyway, the video is titled, "What's the difference between momentum and inertia?" And to me, the word inertia is just useless. They should have never invented it. It doesn't mean anything. It's just the state of your momentum, frankly. I mean, your inertia is, well, what momentum do you have? Period. There, you're kind of done. So it's just another word to describe exactly what your momentum is, so there's no point in having the word because it doesn't mean anything. So they've converted it into some kind of idea that inertia has some kind of meaning, like you somehow resist being changed, and you only resist it based on the size of how much it is, how much of you has to be changed. If you're really small, it's easy to change you. If you're really big, it takes more work to change you. And there's really no resistance to, poor people don't have a resistance to becoming rich people. They just need the rich people to give them the money, and then they're rich. I mean, you can use metaphors that simple. It's just a bank, a piggy bank, and it's not resisting having coins in it. It's just that it has to have an interaction where coins fall in the slot, and if that doesn't happen, then it doesn't collect energy and it doesn't get rich. So I guess the real objective here for him, for physics, for anyone, is to find a nice metaphor that you can use to show how the puzzle pieces fall together. But the trick is that we're more than one system, right? You're the big monstrous thing with the billions of little individual cells, in the soup, in the seawater, and then you can reduce that to your atoms, and then you can reduce the atoms to electrons and protons. And I don't think you need to reduce any further than that in terms of understanding, like if I was to metaphor it, that the electrons and protons are a boat, and the game really is that they're swimmers, in the water, and they jump in your boat, and when they're in your boat, they're rowers. So they're either swimmers or they're rowers. And so you can encounter the swimmers in two different ways. You can encounter them because they're in the water swimming and they're going to jump in your boat, or you can encounter them because you hit another boat, and the rowers in their boat fall into your boat, and the rowers in your boat falls into their boat. Depending on how you hit each other will decide who gets what rowers in the end. And there is a little bit of, the metaphor breaks down slightly, you could argue, in the sense of the rules that decide how they fall requires you to shape the boat in some particular way to figure that all out. Okay, take a little pause. Alright, so as I often do, I'll probably mix metaphors, okay, because I like the currency argument, that this is just about money, and money is motion, and, yes, it has a direction, but the idea really is are you moving or aren't you moving? Is there, when you shake the bank, is there coins in there or no coins? So that works also. But anyway, so we'll play with it, see where it goes, play his video, and I'll just emphasize where, this is where physics sort of goes wrong, in my opinion, and you can sort of identify the places where it goes wrong. And, it's just like the standard model of an atom. I think you can understand that, it just doesn't make any sense that the electrons are spinning around and around at insanely fast speeds, and the atoms are combining with all of that motion and nothing crashes. It just doesn't make much sense. And frankly, you can come up with a much better way to understand what it means to share an electron. Anyway, that's a whole different subject. So leave us begin.
Shop, and today we're going to start doing more of these physics bits. We're going to try and break all this down so it's really easy to understand.
So he generally does like motorcycle engine kind of videos or whatever, or mechanic kind of videos. So maybe he's got no interest in this, but apparently he has some interest because he is making the video saying, underlying physics is sort of important to all this other stuff you do. Understanding the concepts can be quite useful and helpful.
Today we're talking about inertia.
So he's got nice handwriting anyway. Yeah, there's no point in writing words, right? Yeah.
Momentum. What is the...
So one is a real word, momentum, and one is just a piece of nonsense that really doesn't have any use. And momentum equals something, your mass times your velocity, and that'll tell you pretty much how many rowers are in your boat, how many effective rowers, meaningful rowers, and inertia doesn't equal anything. It doesn't mean anything. It's not a real word. It's just a nonsense.
Difference between the two. So this is all to do with that.
So obviously the difference is one is a real concept and the other is just complete mush.
Crazy bastard Isaac Newton, he started all this off, the fucker.
Okay, so yeah, crazy was a fucker and all that kind of, well, he didn't fuck anything actually. The basic rules and the concepts defined were just Galileo started, well, he didn't start it obviously, but it just means you have the three of them, Galileo, Descartes, and Newton, and they just started refining the rules. And the rules are just about how do the swimmers, it's just boating rules, what are the swimmer/rowers doing versus what are the boats doing. And that's really all of this is about, is defining that relationship. And the key, in my opinion, to understanding it is to understand that the boats, the only real boat, are the electron and the proton. And all the other boats are collections of boats, like boats that are tethered to each other as a swarm of boats. So everything else is, the rules for the swarm of boats is different than the rules for the individual boats. They function a little tiny bit differently. Just logically, a dog behaves differently than a pack of dogs, that kind of thing.
There were other ideas before that, but he was basically the one that basically made sense of it all. So that's why we have part of classical mechanics and what's the word now?
So quantum mechanics and Newtonian mechanics really aren't related at all, and Newtonian mechanics have been distorted and perverted by Leibnizian mechanics. So a huge feature of Newton's mechanics has been broken, momentum. So I don't even know why he's typing the word momentum, well, writing the word momentum, when in physics it's been, I don't know, it's been bastardized or it's been turned into a non-reality. It doesn't really equal anything because mass times velocity doesn't equal anything that means anything. It's not a meaningful number anymore because they say there's this thing called kinetic energy that's the real representation of something's quantity of motion, what it really contains, what it really possesses as power, and the ability to do work is defined by 1/2 mv squared, which isn't Newton's mechanics at all. So it isn't Descartes, it isn't Galileo, it isn't Newton, it's Leibnizian. And they never call it that, but that's what it is. And it doesn't have any grounding in any kind of rational metaphor. Somehow you just magically get to have more energy if you're put the energy in a smaller package. The bullet is 1,000 times more energy than the gun recoil. That's the explicit statement by their new physics. And Newton would say, that doesn't happen. The bullet's smaller and the energy is more consolidated into a smaller area. But there's not more energy. I mean, it's, that's the real subject. So unfortunately, if you're going to even say the word momentum, you have to put it in the context of what momentum meant 300 years ago and what momentum means now are two entirely different things, because frankly, momentum doesn't mean anything to the modern physicist. The only one who pays any attention is the NASA physicist, who has to use it because it works. But all the rest of the physicists just play with their abstractions because they don't have to make anything work. They never have to make a 10-ton train going 5 miles an hour. If they did, they'd realize that, yeah, I can't make two of those with one 10-ton train, one 5-ton train going 10 miles an hour. That those two trains have the same amount of energy.
Newtonian physics, that's the one. And why force is Newton's and so on. Which kind of tells you a bit before we even get into it. So,
yeah, but that, whatever. This isn't... Physics isn't Newtonian mechanics. So again, the whole point is that physics is trying to say that Newton got wrong answers when, the truth is Newton basically got all right statements about what the actual world does. And, his speculations about why it does it were minimal.
In basic terms for those guys who, fucking can't remember any of this or didn't even do this, inertia, we can basically say, is mass.
So, again, it's not saying much, because it's not really true. Mass is mass. So inertia isn't your mass. But obviously your mass will decide how much something can affect you. So if I'm the Empire State Building and I shoot a bullet at it, it's not going to mean much. I'm not going to knock the building over. But if it's a little tiny Empire State, little tiny replica, the bullet will smash it into a million little pieces. So yes, mass matters in how you're going to interact with things that have rowers or swimmers. Little boats, can be affected by one or two rowers. Big boats takes a lot more rowers to affect a change.
The mass of something. Now,
it's that simple, really. One person can row a boat, 10 miles an hour. If I want the big boat to go 10 miles an hour, one rower ain't going to do it.
That is not weight, so...
So weight is just when you give a mass momentum. That is, you give it a velocity. So a mass with no velocity has no weight. A mass with a velocity has a weight. So you could just, by process of elimination, understand that, yes, gravity is giving me velocity. So even though I don't appear to be moving, I clearly am moving because I have weight, which means I'm applying pressure. And the pressure is being suppressed because the Earth, is absorbing my movement and then pushing back. So I'm spending part of my time going this way and part of my time going that way. And the only one I can feel is the only one of them is rowers jumping in the boat. I never feel that, The only thing I can feel, is when there's a competing boat and the rowers get exchanged. So the ground is a competing boat. I hit the ground, the rowers exchange. I feel that because it's uneven. My ass, in this case, gets hit with all the pressure and it has to spread it to the rest of my mass. And so I feel it because different parts of my body are getting pushed on at different rates. But the swimmers, they jump in from all places at once. And so I don't feel any difference. So there's no way to metaphor that perfectly. But the reason why you sense motion is because of uneven application of it. If I apply the motion evenly to all of your cells at the same time, you're not going to feel it because your nerves aren't made to feel it. You can't feel even pressure. You can only feel it when it's uneven. And so that gives people a false impression that they're only being affected by one force in the circumstance of gravity, and they're clearly being affected by two different actions. The action of you pushing into the earth, and then the action of the earth pushing back.
It is not weight. Weight is basically what you experience in a gravity.
The reflection, you could argue. So that's another part of this where, you know, you really need a metaphor that gets to the idea that, you know, energy can hit something and it can go with it, right? Or energy can hit something and it can bounce off. You know, or energy can hit something and then both things with a less velocity or less energy move. And the argument is on the subatomic scale, on the scale of electrons and protons, that action has rules, and those are the only real rules. But the fact is that when you put electrons and protons in collectives, you tie them to each other through charge, that they will absorb the energy differently than electrons and protons do explicitly.
Gravitational well, so on Earth, on Mars, on the Moon, weight always changes where the mass of an object, unless you chop it in half, doesn't.
So yes, our weight is just a statement of what our mass does in the force of gravity. So how much motion, how much momentum does our mass have in gravity, and we call that how much do you weigh. But it's really just a representation of how much gravity you can collect. So the mass is your bucket. It's how big a vessel you have or bank. And you're just saying how much can I collect, and how much I collect based on how much mass my bucket has decides how much pressure I can apply to something I encounter, how much, how rich I am.
Mass, in a sense, is how much stuff. And when we say
stuff, you could just say boat, or you could say bank, or you could say vessel, or you could say, or you could use lots of words for what the stuff represents, but the stuff is going to get pushed by the rower or the swimmer, and it collects it. It's either in the boat or it's interacting with the boat. But I'm just saying that's the matter can basically preoccupy the force in the emission of pushing it. So maybe this is a good place to just draw the what I would claim is the real way that electrons and protons acquire momentum or motion. And it always has to be understood that that's what's really going on. So, yeah, we'll do that. All right. So I would contend, always something. All right, that if there was an electron is sitting in a sea of energy, everything is. The universe has got a bunch of these swimmers, okay, swimming around, and the fact is that if I put you in some deep space away from all other objects, the idea, you know, right in the middle of the universe, so to speak, the idea would be is that you'd get hit from both sides with an equal amount of stuff, and so at best you could just jiggle, but you wouldn't be going anywhere. And what you need is a differential, okay, where you start to collect motion in a direction. So that just means that you literally are collecting it. So let's say something hits you from this side. The idea is electrons and protons, that piece of energy is now a unique rower. It went from being a swimmer to being a rower. That's the rule. So now it's pushing, okay? It's making the matter move. And the matter's not going to move the same speed as the rower, because now the rower's got a big giant mass to push with it. So it's going to go some percentage of its original speed. And that rule applies to even bigger objects in the sense that you have to spread the momentum of the thing that hits you with you. And so the rower has a certain amount of momentum. It has a mass and a velocity, okay, that equals a certain amount of Planck energy, we could say. And all you're doing is collecting that quantum of energy. So quantum mechanics as a term makes sense because this is really just about the value of a rower. All right. Well, anyway, so a rower hits you this way, it sticks to you, and the whole thing moves this way at some reduced speed. Well, the idea is if I hit something coming or just existing here, the idea is when I make that contact, what's going to happen is just like two Newton's balls hitting each other. There's just going to be an exchange. That is, this one's going to take this one's motion and go this way, and this one's going to take that one's motion and go this way. And it doesn't matter whether you think about them going through each other or you think about them bouncing off of each other. The idea is this is leaving this way, and this one's going to leave this way. And now this is back to its original state where nothing's happening. You know, it's got nothing. It's collected nothing. And then the argument is that you can collect rowers in only one direction. So let's just say you had 12 seats, you know, in the boat. Okay. The idea would be, so it could be 1,000,000. You know, 1,000,000 places on the surface of an electron where it can collect a direction. And all it's really doing is it's just saying, okay, I can only have one on this side if there's none on this side. And I can have 2 on this side if there's none on this side. I can have 3 on this side if there's none on this side. But let's say one hits from this side now. Well, then this last one leaves. So now I'm back to 2. But I'm never going to have one on this side and one on this side. That'll never happen. So the clock at any one time can only have 6 of the seats full in terms of a direction. Okay. So it could have 3 this way, and it could have 6 going this way. You know, it could have 1 over here and 1 over here. You know, this opposite one couldn't exist. So wherever there's 1, there can't be any on the other side. So you just have to put like an X on that side to understand there can't be one on the opposite side. But the point is the electron can literally have more than one direction, and it will actually travel in that staircase. If I gave an electron a direction this way, you know, I collected energy this way, and I collected energy, you know, this way, it literally goes this way and this way. It goes both directions. So if it's moving, it's really moving in some kind of staggered kind of line, and yes, that will look like this, but it's not literally what it's doing. Where an atom or a more complex pile of this stuff could literally travel this line, because it can have one atom going this way, another atom going 3/4 that way, and it comes out to 1/4 this way, and it sort of does the math, and it ends up, you know, creating an overall velocity, because the object itself jiggles and does the math and then moves the path. That's the net product of the math. So really, you do have to understand that the atomic world, the universe, is electrons and protons. Everything else is sort of an abstraction. Everything else, this is the first and only universe. The one with the little boats and the little swimmers, that's the only real universe, and the rest of the universes are just, you know, you're just watching the yacht club. You're watching something, you know, on the bigger scale. So it's like a city diagram is the houses, you know, and the garages and the driveway and the yard and the lot, you know. That's the real city, and it's just made of a bunch of those units, you know. So any kind of metaphor that understands there is a real unit that things are made out of, and it's little tiny electron proton boats and swimmers / rowers. And that's the real one universe there is, and everything else you see is just when all of these things get in a group. Because you don't see the real universe, because there's no way to see it, because you can only see it by throwing a bunch of swimmers at it and seeing how they reflect. And so when you throw a bunch of swimmers at it, it all of a sudden is gone, and obviously you can't see it because you threw swimmers at it. Alright, anyway. We'll see if that was helpful. Well, we won't see it. It happened in the smallest universe, and you really won't see the impact. Anyway, let's just play along and continue.
We mean matter, and when we say matter, we mean atoms, basically.
Okay, so you don't mean atoms. You mean the smaller bits, the Planck quantum bits, the stuff that's really in the empty space and it's really indivisible, the stuff that really doesn't break into little pieces and doesn't do any kind of nonsense, the stuff that really decides what quantum means. Quantum of energy, quantum of mass. That's what you're seeking, and you have to go one more word, all right, to get that right. That the charged elements are really the electron and proton. Again, the 400 other silly particles are not real things. The only thing that really exists are electrons and protons, and neutrons are a dipole. They're a proton and an electron.
Oh, hadrons and baryons and blah 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 blah. But anyway,
yes, exactly. Blah 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 blah. Physics shouldn't even play with all these idiotic words that really don't describe anything real. It's just all bullshit. There's positive and negatively charged objects. They inversely react to a field you produce. So you produce a field. I put an electron in the field. The electron does the opposite of what the proton's going to do in that field.
That shit bit out. So yeah, so inertia is about mass. It's not the mass. It's how much stuff there is matter, which is basically atoms, the stuff you have.
But there's no inertia. There's just the simple point that one rower can make a boat go a certain speed, 2 rowers make it go faster, 3 rowers make it go faster, and it's just about how many rowers you can fit in your boat, and how fast you're capable of going based on that. Something like that.
Well, inertia is the base. How can I describe this? If you have a ball and this is steel, it's a steel ball.
Yes, you're not going to come up with a number that says this is what its inertia value is. You're just going to state what's its momentum. So again, it just doesn't mean anything. There's no formulation for inertia. Inertia it's not a concept. It's a useless word, a redundancy. Your inertia is your momentum. Whatever your momentum is, that's your inertia.
This ball, and let's just, the weight thing, let's just say it has a mass of 1 kilograms. This ball will require force to move it, to change its velocity.
You have to have a rower or your boat doesn't move. So yeah, and if your boat's moving, you have to have competing rowers to change the movement. So again, that's sort of the rule. If I'm an electron and I'm moving and I encounter a rower, a swimmer, I'm not gonna. He's not gonna get in the boat. Okay, so that's the rule. The only way it gets in the boat is I have to be going the same way the swimmer's going. If I'm going some opposite way the swimmer's going, you sort of understand. If you're swimming, you can't jump in the thing that's attacking you. So you have to bounce off of it. It's that kind of simple rule. And the only way you can jump into the boat is to sneak up behind it and jump in.
So let's say its velocity is 0 meters per second. That's wrong, fucking hell. 0 meters per second, there we go. Its velocity is 0. This is what we call the rest mass.
So, yeah, and another concept that doesn't mean anything. You have a mass. It's the size of your bucket. The mass is always 0. Okay, in the sense it doesn't mean anything until you give it velocity. It has no momentum without a velocity. So it doesn't matter as a concept. It doesn't have any meaning until you put velocity in it. Until you put some rowers in a boat, the boat is meaningless.
And we have to apply a force to this to accelerate it, to basically change.
So we're applying a force that's, again, the application of force just means we're going to encounter a bank that has a different amount of money. We're going to encounter a boat with a different currency in it. The currencies, the clock has rowers in different positions. And so it's different than our own. That's the only way we could hit it, is it has to be different than our own, right? It's impossible to hit something that's running a parallel line with you. So the only way you can hit it is it has to have some sort of difference in its arrangement of rowers than your arrangement of rowers. And then if you interact with it, there's going to be rules about how those rowers in the bumping are exchanged. But all the rowers have to be accounted for and are conserved. And they're all momentum rowers. There's no kinetic energy rower.
This velocity. So we want this force to give it a a change in velocity over time.
So that's Newton's formula. So Newton didn't say F equals ma. This is what Newton said. Force is a change in your velocity over whatever time period you want to test it in. So you could test it in 1 second, you could test it in 5 seconds, you could test it in 5 hours. It's just about the test, and the F number you get is a rate because you put time in the bottom of the equation. But if you just want to know what was the total amount of force, you just cross the time out because it becomes a 1, the total amount. So there is no rate. Okay, so you get a rate number if you put a time in. You get the total force if you just ignore the time factor. So it really is just saying F equals V, the change in your velocity, because you know the mass is a constant. You're not changing the mass in any of these. When boats hit each other, they don't exchange mass. They exchange rowers. So the only thing you're exchanging are the rowers, and the simple truth is Newton knew that it's going to tell you how much force there is going to be told by you having the size of a boat and a speed. And you can know exactly how many force bits, how much force you have, just by knowing, and how much you've encountered in your voyages by just understanding what's your velocity and what's your mass. And that equals your force. So it's really just saying force equals momentum. It's really saying that. It's just mass and velocity.
In time, this is basically equals an acceleration.
So acceleration is the tiny portion of stuff that happens while you're interacting, and so that can happen in a billionth of a second, or that can take 10 years to happen. Acceleration doesn't mean anything in the sense that, yes, there's different rates for all the different things, but from the electron's perspective, he's either got a rower or he has no rower. There's nothing in between. So the issue of acceleration doesn't really exist because it's either being pushed or not being pushed. There's no resistance to pushing, there's no friction, there's no air resistance, there's no elements that are stopping it from moving. So when the thing interacts, both of them just start going. And if you did the experiment in space, that's what you'd find happens. You could take something that weighs 30 pounds going 30 miles an hour and hit something that's 90 pounds, and they'll both stick to each other if you make them stick, and then they'll both go off at whatever 120 pounds spread over the original 30, which means you're going 5%, 1/5 of the original velocity. And so it's that simple. But there's no acceleration issue because there's nothing resisting the fact that the rowers just are rowing, and they row right into another boat. So the boat hits, and the rowers just jump into the other boat and start rowing. I mean, there's nothing resisting. And that rowing motion gets them, they're at the speed already. I mean, the only thing that's happening is you're just taking a bigger boat, and you're just saying, well, how many rowers does it take to make that boat move at that speed?
So we need to we need to apply forces to move stuff. The more mass...
To change how it's moving. So again, every interaction is either going to change how you move, and there's really no way to have an interaction that won't change it. Because if you hit something that's doing exactly what you're doing, then you're not going to hit it. If it's doing exactly what you're doing, you can't hit it.
Something has, the more force is required. Now this is obviously basic stuff. You try and push a lorry or push a beach ball. So its inertia is its resistance to move.
Alright, so there's no resistance. It's just that you have to give away your rowers if you're going to move somebody else's boat. That's the rule. So you get poorer because you gave somebody rowers, or vice versa. But there's no resistance anywhere in the system. and until you start talking about friction and the rest of that stuff, and that's not a resistance, that's holes in your bank. That's a hole in your pocket. You have change in your pocket and there's a hole in your pocket. That's friction. Friction is giving away your money. Put simply.
What is important here is it's a vector quantity, which basically.
So he's using the what he's been educated to say, which is just sort of silly. Energy always has to be a vector quantity. It's always in a direction. It's an arrow. It's a swimmer. It's a rower. It doesn't go in any direction. It goes in a specific direction. It's always a vector, whether it's in the form of this fake kinetic energy. A 10-ton train, by kinetic energy's definition of how much energy it has, or momentum, it's the same damn train going down the same damn track. How can you say, well, its kinetic energy is in any direction? Well, no, it isn't. It only has energy in one direction. It weighs nothing behind the train or above the train and all these other places. It weighs nothing. The only place it's going to weigh something is in the direction it's moving. That's the only direction it has any rowers to give.
Basically means that you have to apply a force to make it go that way. If you want to make it go another way, you also have to apply a force, because it will resist doing that.
So it really won't resist anything. So there's no resistance in space, in the real physics, in the real physical universe inside of us. There's no resistance to any kind of motion. There's just an obligation to put a rower in a boat, or the boat's not moving.
If you get, I was going to say a ball, but if you get a conrod and you fucking leg this out of the ISS, or maybe you're going to...
Right. And so this is not an object made out of the elemental universe. This is a more complex object again. And the fact is that you could theorize that if I have two of these things, and one of them I throw out of the space shuttle and the other one I keep in the space shuttle, that the two objects, if you really could look at the electrons and protons, and you could see what kind of motion they had, that you could see the difference between the two objects. That you could look in the boat and you could see that this one has rowers doing this and that, and this one has rowers doing this and that, some other arrangement, and that they're not the same anymore. But the fact is that when you have a collection of boats, like a school of fish, the school of fish moves, but it moves based on a net product of how much fish is going this way versus how much fish is going that way. So the same thing happens with any big object. It's not so much what each individual boat is doing, it's what the whole collection of boats is doing. So yeah, there'll be some atoms going this way, and there'll be some atoms going that way. And your net motion might be in that direction because there's more little bits moving that way, more rowers rowing that way, than there are rowers rowing this way in the entire collection.
Interstellar space, wherever, and you chuck that rod in space, this rod will continue to fly through space forever until something affects it, or the...
Yeah, so these are all arguments they really don't go into enough detail with, because obviously I think we already know that empty space isn't completely empty. And the fact is that as the thing's traveling through space, it's going to hit more atoms in the direction it's going. And slowly, but methodically, it will be arrested. Its motion will be consumed by that tiny amount of friction. So even the idea that it goes forever isn't really true, because we know space isn't entirely empty. And so it's going to give away its motion to friction. It's just that the friction is very tiny on the scales that we look at. We are seeing, throwing a bunch of vacuum cleaner dust at a car. Yeah, it's not going to slow it down much. But the fact is, it does slow it down.
Half-life of protons makes it dissolve after trillions and trillions of years. But yeah, you throw it and it'll carry on going until something either gets in its way or applies a force to it.
So until it has an interaction. So it either has to have an interaction because the field, the ocean, actually has more swimmers in it, because there's some charged object, or some, in the case of the wrench, there's some gravitational body creating a current in rowers, swimmers. So because there's a gravitational body, there's more swimmers rowing, swimming in that direction. So you end up getting pushed by the gravitational field. But all the gravitational field means is that there's more swimmers swimming towards than there are swimming the other way. And so you're going to gradually collect rowers in the direction the swimmers are swimming. So you're going to collect free swimmers. Okay, you're not going to get your rowers because you hit another boat. You're going to get your rowers because the swimmers are changing what's in your boat, because there's more swimmers hitting one side of your boat than the other side of your boat.
It will just continue to go. As long as it doesn't hit anything or go too close to stars or whatever, because of gravitational wells and all that kind of shite, it will keep on going forever. And you have to apply a force to it.
So there's no such thing, right? There's no place in this universe where this works, blah, 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 because every time I actually throw a wrench into space, the fact is it's already in a field that's, got all kinds of inequities in it. There are, in fact, unequal. Like a star billions of light years away, the fact that I can see the light means I'm seeing an inequity, a disproportion. It should be dark, because on the other side it's dark where that star is. That kind of argument can be made. So I'm getting hit with more energy from this direction than I am from the opposite direction, so theoretically I'm going to get pushed by that light. Well, gravity works the opposite, so you're just saying it's the opposite scenario. If there's a star over there, there's a subtle change in, there's 1 in a billion more swimmers going this way than that way. And that 1 in a billion difference means I'm going to have 1/billionth of the time, I'm going to have more rowers going this way than that way.
To make it change direction. And you might think, well, this is all basic. Why did Newton have to write all this stuff down? Well, because, it's like when you spin something, it will eventually...
So he should have never gotten into spin, because, yes, that's angular momentum. Slightly different, but it's really fundamentally the same rules. It's just that obviously you keep changing the direction a piece of matter is moving. So, and the obvious point you could also make is it sort of illustrates that the direction that something's moving can be changed for free. It doesn't cost anything necessarily. It can cost something, but the fact is you can change something's direction without consuming any apparent energy.
Actually slow down. So why is it slowing down? Why is it changing velocity? Why is it accelerating? It's slowing down. Because obviously something, air resistance, gravity, and
gravity's doesn't mean anything to this. If I'm spinning something, technically the gravity resisting the motion up is the same as the gravity giving you motion down, so it's a net zero. So it's not costing you anything, but the air is, okay, and that's a fact.
The gravitational load is basically forcing it into its bearings, which is...
So that's the trick, right? So the point would be is if you're spinning it in a gravitational field, what I just said isn't really true, because the motion down ends up leaking into the ground. Some portion of the energy you're getting pushing down is lost because the bearing's going to hit the bottom and waste some of your motion in terms of vibrating the ground. But the bearings can be well enough made that the energy going up, the pushing the bearing up, balances those two, and you end up especially like fluid bearings. You can create a bearing that really the friction is just the friction of the fluid molecules, because the metal never hits the metal. So you're reducing the how hard the boats hit each other, and if you can reduce how hard the boats hit each other, you're going to reduce how many rowers are going to get displaced.
Friction. And friction and stuff like all these parasitic losses, that's why it loses its speed, loses its velocity. It starts to accelerate, which is slowing down, and so you can tell there's a force acting upon it. If you know that things should just carry on going the way they're going, that's something spinning is rotational inertia, which we'll get to.
Right, so I'm just saying this does complicate, because obviously the faster you spin it, the less friction there is in the bearing. And then you're really just talking about the oil or the fluid the viscosity of it. The only friction you have is in the motion of the liquid. And even that motion starts to become meaningless because, you know, once you get it moving, it gets up to speed. You don't have to add any energy to continue its motion. So the bearing can be quite efficient, and you won't lose any or much energy at all to the bearing. But yes, it's more, you know, why make it more? The fact is the air molecules are sticking to the surface, and the air molecules are being moved and they're being thrown into space, and so that energy is being lost. Those rowers that row the air molecules into the air, those are rowers you lost, the system lost.
So what's the difference between this and momentum? So
now it's time for ice cream.
So I guess this was we call it some kind of humor thing. Yeah. So anyway, then he ends it with this, you know, little setup of a kid playing with his father's drum set, I guess.
Imagine if manufacturing...
commercial right in the middle of that, so that's unfortunate. All right, well, I'll pause, get rid of the commercial. Okay, we'll finish the joke.
if we look at the equations,
so you
of
could have
these things,
fallen for that, right, as a joke, if they didn't do the microphone falling down. You know, you could have, you know, it could have looked like a real instead of a setup and a fake, if they just didn't do the microphone falling down. Yeah, because that was like, well, what is that, a coincidence or something? What is, yeah, didn't have anything to do with it. Yeah, so that was sort of bullshit, but whatever. Okay. Yes, it's necessary to be entertaining. That's just another video people should keep making, saying, why the fuck does everything have to be entertaining? Does everything have to be, you know, put into, you know, baby talk? You know, immature, drunken physics. I mean, you know, the whole thing is just so discouraging.
We're on there. Inertia is basically the force that we require to move something, and that is our mass times our acceleration.
So that's the useless part. So he's just talking the religion now. There's just, yeah, obviously the force, you already pointed it out, is the velocity times the mass. The force is the momentum. The momentum is a direct product of whatever force you collected. F equals momentum, P equals work, equals weight, equals pressure. They're all exactly the same thing. They're just how many rowers are in how much of a boat. Period. Mass times velocity. It's a momentum universe. Everything's just about momentum and exchanging your momentum. And your momentum is how much boat, how many rowers. Nothing else.
Because it's an acceleration, because we can't just instantly go from 0 to 10 meters per second.
So whether you do it instantly or it doesn't really make any difference. I mean, it really doesn't make any difference, because you're talking about this subtle process of, you know, I bang two boats into each other and the rower's up in the air and he hasn't landed in the other boat yet. But that's where he's going to be in a millisecond. So what's the difference? It really doesn't, you know, oh, and he has to put his oar in the water. Yes, he has to do all that. Yes, that process has to take place, but it's meaningless. And on the subatomic level, it's meaningless. If you have the pusher, you're going as fast as the pusher pushes. You know, the pusher weighs 10 pounds, you weigh 100 pounds. The 10-pound pusher will give you a certain amount of motion, a certain percentage of its velocity. So the 10-pound thing going 100 miles an hour hits the 100-pound thing, and it's going to go at 10 miles an hour, that kind of thing. You just do the simple spread the money over the surface. And to spread over a big surface, you have to turn into dollar bills. To spread over a smaller surface, you could use fivers. A smaller surface, you could use tenors. You know, even smaller surface, you could use 100. You know, so how big the bill is, how big the velocity is going to be, is how small did I have to make the denomination? How small did I have to make the coin that's in each boat?
have to go from 0 to 10 meters per second. So that means that there, in the velocity, there is a change over time, like so.
So again, and the time is irrelevant. It's just if you want to know the rate of the force, and you want to say, well, it's 10 meters per second, or you want to turn it into 60 miles an hour, you want to put it into a rate, then fine, use time. But if all you want to know is how many calories is it, right? Not how many calories per second. Yeah, you just ask the simpler question. You just realize that the force is going to equal the total change in your velocity. So find the end effect on you, and that'll tell you how much force affected you.
All is wonderful, absolutely great. So basically inertia is the resistance to want to do this.
No, there's no resistance. Again, it's just there is no resistance. It's just that you have to either have somebody give you rowers, or you have to go steal them from somebody else. But that's the only way you can play the game. You're a boat. You're in this ocean. Yes, you can find a gravitational body, and that'll get rowers into your boat because you're in an uneven. There's more. They're not banging into each other. There's more coming from one side, so they settle in the boat, and you can gain rowers that way. So you can jump off a cliff and gain rowers from gravity. But as soon as you hit a surface, you're going to start losing them. That breaks your bank, and you spill what you got. So your boat stops every time you hit a big rock or something. Yes, the rock will take, all the rowers will fly out of the boat and be sitting on the rock. They're not going to be in your boat anymore. So, there's all ways of trying to metaphor this exchange process, but that's all you're doing is exchanging quantum of energy. Rowers, swimmers, things capable of pushing at a constant amount. They're a penny. You're exchanging really pennies. So you can exchange a dollar bill, you're really exchanging 100 pennies. Or whatever they are. Yeah, I don't remember some word for it in British lingo.
And that is related to its mass and then how much we are trying to accelerate it. When we look
So again, the acceleration is just the process of getting to your final product, which is your velocity. And in most cases, 99.99% of cases, there's no such thing as a constant acceleration or any of that mush. The fact is, you have an interaction, you have a pretty immediate interaction in the sense that the exchange is made, the acceleration is over, you have a leaving velocity, it has a leaving velocity, period.
momentum is mass times our velocity. Oh, I should put little times in there, just to make it clear for people. Our velocity. Now, our velocity has a vector.
So again, it's just this F does equal this P does equal, all of it. Weight, pressure, all of the little symbols, they're all representing a single thing called energy, and the energy is quantizable and understandable that it's in bits. It's in bits of energy. And all this system is about is collecting the pennies. And the pennies can be in the form of a $10,000 bill, but the fact is, it's all just pennies.
Our force has a vector. All these actually, acceleration has a vector as well. These are all vector quantities.
So again, more talk about vector. Who cares? It's not a real concept. Of course, all energy has a vector. There's no such thing as energy in every direction. It doesn't happen. The little bits are quanta of energy in an explicit direction. That's why there is gravity. That's why there is charge. That's why there is all this stuff. It's because the stuff that makes it up has a direction. The rower's rowing in a direction, and it only rows in that direction, and it doesn't do anything else.
Vector meaning that it has to have a direction. It can't just be anywhere. So when we look at these,
well, clearly kinetic energy can be anywhere, except it can't. Okay. The 10-ton train going 5 miles an hour down the track, its kinetic energy is going exactly the same direction its momentum is going.
Momentum is it's the quantity of motion, basically. Oh, okay, now can't write anymore. Quantity of motion.
All right, so that was Galileo, Descartes, and Newton. I think they all used that phrase. So that was the word for energy. So instead of saying energy, because it didn't exist as a word yet, or kinetic, you said quantity of motion, an amount of motion. And that's exactly sort of what momentum says. It's an amount of money. It's the currency of action in the universe. So if you want action in the universe, you have to have currency. You have to have pennies or dimes and nickels, quarters, dollars, $10 bills. You have to have the currency to have the motion. No currency, no action. Nothing ever hits anybody. Nothing ever happens if stuff doesn't have the pennies of rowers.
It's not the best description, I know, but it will do.
So again, it's not really a description. It's just another word that defines the thing. So you might as well make it one word. Quantity of motion. But yeah, it doesn't sound as nice as energy.
So let's just take two things, for example. Let's just say we have a block here that weighs 50 kilos, kgs, and we have another block here that weighs 20 kgs.
All right, so I won't bother with the rest of this just because he doesn't really say anything, and these are really poor analogies. 50 and 20 could have been 25. And if he gave them different velocities, then this would have been interesting, because then he'd have to say, well, if I change the velocity of the lighter object, somehow if I have a 50 weight going 25, or I have a 25 weight going 50, that somehow this thing, even though they have the same momentum, one of them has twice as much energy. And then you have to explain why physics is stupid enough to think that's the truth, when there's just no good reason to think that's the truth. Momentum is the right answer. It's the real thing. And kinetic energy, 1/2 mv squared, is absolute fable. There's just not anything about it that's good. It's all bad. It just makes messes. It just breaks the continuity of everything he said in this video. And it'd be interesting to get him to talk about that. Where am I? Yeah, so let's play a little bit of it.
And we are moving them along, so we have a vector at 20 meters per second. You see all that? Only just 20 meters per second. Like so. So what this means is, if we look at the equations above, our mass is higher for this one than it is this one. So we are going to need a lot more force here to accelerate.
So you need more rowers in the bigger boat. But the fact is, the bigger boat with more rowers will have more energy. So you have a bigger mass going the same speed as the smaller mass, then obviously it's going to have, like I said, if you made this 25, then you'd obviously say, well, the big boat going the same speed must have twice as many rowers. There's twice as much mass. There has to be twice as many rowers to go with the twice as much mass to go the same speed. So it obviously has twice the energy, period.
This up to 20 meters per second. That's our inertia bit, because it's heavily dependent on mass and the acceleration. Well, the acceleration, we're trying to go from 0 to 20 meters.
So again, the acceleration is meaningless to any understanding really of energy, because acceleration is just it's just the exchange portion. It's just the noise of the actual exchanging, but it doesn't have really anything to do with what the end product is, which is just your velocity. How much does the boat weigh, and how many rowers are rowing in a direction?
Per second. So there's our acceleration. So if we want to go faster, if we want to accelerate to a higher speed, then the force is going to be bigger.
And so the acceleration is just as well understood as a deceleration. So you're just really saying, how much money do you have, and period. Do you have an exchange where you're gaining rowers, or do you have an exchange where you're losing rowers, period? Are you gaining money or losing money in the transaction? There's just no need for any concept of inertia or resistance.
If we have bigger mass, then the force is going to be bigger. Same with this one here. If we look at them, this one has less than half the mass of this, so the force required is going to be less. when we look at
the force required to go the same speed. Right. Because there's less boat to push. Period. So, duh. But there's nothing called inertia.
momentum, though, on the other hand, now we have a block that's 50 kilos going 20 meters per second. So it's our mass times our velocity, which means that our momentum, our P here, is going to be a higher quantity than this block that's 20 kilograms going at 20 meters.
Right, and if you just did this example by changing the velocities, then you'd be in big trouble, because momentum's going to say there's a certain amount of quantity of motion, and then kinetic energy is going to say there's a different amount of quantity of motion. So the idea of understanding it as a quantity of motion doesn't mean anything in physics, because which one is the right answer? Is momentum the right answer, or is kinetic energy the right answer? I clearly would argue momentum was always right. Newton, Descartes, and Galileo weren't idiots. If there was an mv squared, they would have noticed it, and they would have told you about it. And they didn't tell you about it, and then they told you it was nonsense, and you didn't pay any attention.
You know this. If you have a motorcycle, a scooter going 50 mile an hour into a brick wall, or you have a bus going into a brick wall, one
bucket has a lot more water in it, so you're going to get a lot wetter, and it's just that simple. So yeah, we don't need to do this part. All right. So anyway, interesting fellow. It'd be nice to see if he's willing to do any conversational exchanging videos, but like I said, it seems like he's trying to build a channel more about applying physics to the specifics of engine performance and whatnot. So, but we'll see. Couldn't hurt to try and see if there was any point to it. So, there's always a point. I'm just saying that, see, people diagram something, and you can see, in my opinion, there's obviously flaws in the diagram. And he's not really telling us what physics says, because when physics says F equals ma, they're saying A equals velocity squared. And that's the big, monstrous mistake sitting right in front of everybody, because it's not. The fact that we're moving 9.8 meters per second, every second, doesn't mean you square our velocity. There's no point in squaring 9.8 meters, because I could be in gravity for 2 seconds, I could be in gravity for 10 seconds, I could be in gravity for 600 years. No point in saying it's my velocity squared. No, it really isn't. My acceleration squared. Alright, so enough stated, I think. Alright, so till the next time, this has been a draftphysics.com, debatephysics.com. Oh, shit. The microphone's not working again? Oh, I think it is. Okay. It better be. Bastard. If I lost 2 videos, I'll really be pissed. Anyway, alright, so till the next time and such.